Okay, then maybe we can get started.
Mhm.
So it's my pleasure to introduce today Jens Rademacher to you, who will be telling about chaotic front motion in Allen-Cahn equations with large-scale linear fields. So I'm really curious about this topic, but I must confess I'm not very familiar with it. So please, Jens, teach us. The stage is yours.
Yeah, thank you very much.
Thank you.
Yeah, thanks very much for the kind invitation. I hope I can give you a little bit of background on this. Feel free to interrupt me at any time or ask questions. I'm not 100% sure about the time, but it should be less than an hour, right? So this is the
like around
order.
1 hour. Around 1 hour.
Yeah,
But
exactly.
we can help you extend it.
Yeah, we can ask you questions.
Well.
Yeah, like a piano style internal seminar.
Oh, great. Yeah, okay.
No, over
We'll
seminar,
see.
not internal seminar. Too much. Yeah.
Yeah, okay. So can you see my mouse pointer, by the way?
Yes.
Or no?
Yes. Yes. Yes.
Yes. Okay. All right. So this is what I talk about today. Joint work essentially with Peter van Heister on the left and Martina Chelus-Bruckner on the right, and it builds on earlier work with Arjen Dulman and Hideo Ikeda. And yeah, so what I'll be talking about has to do with reaction diffusion equations in one space dimension and the interface or front formation there. So this is kind of the simplest setting at first, and we're interested in how these interfaces move. And here's just a little bit of an overview over historical models, just to give you an idea, if you are not familiar with this, what are the equations that I'm looking at. So on the top left, this is the classical Fitz-Nagumo system for modeling nerve axons and nerve conduction. And what I want to point your attention to is that here we have this nonlinear part. The only nonlinear term is this U cube here, and everything else is linear. So the coupling to this second component W is linear, and the second component W solves a linear ODE actually in this case only. There's also the so-called doubly diffusive version of this, where there's also a diffusion here in the second equation. The way that this is written is a bit funny because this diffusion is here, right? So this is the second order derivative on the left in this form. So this is kind of the classical form, and this cubic nonlinearity is very typical in other cases, and we'll get to where this comes from and why potentially. Let me just continue with the model classes here. So on the right, there's a model by Hackberg and Maron, which also has this cubic nonlinearity. All other terms are linear, slightly different form, but here you already see this doubly diffusive nature. And then there is a more general class of equations that Ikeda and Nishihara have looked at, where these nonlinear terms or this coupling is more general. And this, however, is on this slide here because it already shows the scalings basically that I want to be looking at. In particular, there is this epsilon squared here in front of this diffusion term in the U component, which will be important, and it's not there in the V component, right? So there's a spatial scale separation between these two. And also the way that this is written, there's a temporal scale separation due to this factor here, which is not in the second equation, right? So you can think of this tau here to measure the relative time scale. Is it working with the slide that you see the pointer, etc.?
Yes, we see the pointer.
Yeah. Okay, very good. Yeah.
Very well.
Okay, and then and what happened is that it turned out that some of the phenomena that people see or want to model do not really work in this class of two-component systems. And then there was a suggested three-component system, in particular in this group by Hans-Georg Purwins, who's this last author here, which is a generalization in some sense to three components. All have different diffusion rates possibly, but it's purely diffusive. And there are also these time separation parameters on the left. And these right-hand sides feature these F, G, and H, which in this case are, again, that this first component has this cubic nonlinearity. The coupling is linear, and all the others are linear as well. Right, so in some sense, what I want to convey here is that it's a broadly studied class of equations has this feature of one component which has a cubic nonlinearity and the coupling to the others is linear. And what one sees then is such front formations. That's the one that I want to focus on. There's lots of other phenomena in these equations, but here's in particular what I call a front. So here you see a space-time plot. Space is in this direction to the sides, and time goes into the back, and the vertical is the amplitude. So here you see a relatively constant state, then there's an interface, such a front, and then there's a constant state on the right. And this interface here is now moving in an oscillatory fashion. The goal is to understand such phenomena from a rigorous mathematical viewpoint. That was also kind of the starting point when we looked at this way back. And lots has been found, of course, but I want to illustrate the results that we have found. And the class of equations that comes out of this is of this form. So we have this first component with this cubic nonlinearity. This is coupled now in a more general way, possibly to other components called V. So if there's no index, this is just the vector. So this G depends on the entire vector of these, what I call slow fields, which are these V components, and they satisfy this equation here, which is linear as in the others. And if you would now remove this G, then this first component could be completely decoupled. And this is what's the classical one-dimensional Allen-Cahn equation, which was also the core in the other cases, as we saw. And then there are these linear equations, and these linear equations you can think of as basically heat equations with a stabilization, because this Vj factors into this with a negative coefficient. Yeah, so it's epsilon scaled, but never mind, right? So this is negative, so that kind of stabilizes this in addition, but then there's a driving by this U. So in that sense, what happens is that the Allen-Cahn dynamics from this first component is fed into the second class of components, and these are following this like in a heat equation. So they can be viewed as refractory variables, and this is also the role they played, say, in this Fitz-Nagumo equation. So these V's are kind of slow refractory variables which kind of follow essentially what has been imprinted by the U. On the other hand, there's a coupling back in this case, right? And this is the interesting part, which I'll talk about mainly here. What's the role of this coupling back and what's the impact it has? But for the moment, let's focus just on the class of equations. So for n equal to 1, you can view this as a doubly diffusive Fitz-Nagumo system. For n equal to 2, it's this Purwin's model for gas discharge. I didn't mention it, but the physical background is gas discharge modeling. And for n equal to 3, you can think of it as a kind of fully diffusive Hodgkin-Huxley equation. And the solutions look like in this. If you just take a snapshot in space-time, one has these thin lines which come from this Allen-Cahn equation. I'll talk about more what this where this comes from in a moment. And then there are these thick lines which come from the V, and they have much smaller gradients. Yeah, and the reason for this gradient difference is this scale separation that I didn't talk about yet. So this is going to play a very important role. This epsilon factor in front of the U generates sharp interfaces. And although there's an epsilon appearing in these other equations as well, it appears on the full right-hand side. And that means you can kind of divide by the epsilon squared and put everything on the left-hand side. And then you can see that really the V and the U live on different spatial scales. The U has a kind of this small scale and the with sharp interfaces, sharp gradients, and the V's, they have large scales with low gradients. Okay, and here's just the first result without much detail. I think I won't be able to talk much about the techniques really, but rather focus on the results. That is just saying something about the fronts themselves. So what I'll talk about is just single fronts, just single ones, right? In the previous slide, there were multiple fronts. I won't talk about this. I just talk about things like this where there's a single front. So like here, it's the black component is this U component. It's near the near -1, I'm sorry, and on the left, and near +1 on the right. and these other components follow up on this, right? This is this refractory nature. And the first result here is just talking about the existence in a general sense. So for low component numbers, this has been done before, and here we just generalize this. But what I want to point out is that in this bifurcation theory business, one writes this as a spatial ODE, and you think about it as a heteroclinic connection in space. That's kind of the language and the setting. So this is a result about heteroclinic bifurcations, and it is in a so-called singularly perturbed context here because of this epsilon scaling parameter. And then what happens in this bifurcation analysis is that you basically aim to translate the differential equation problem into an algebraic equation. That's happening via so-called Lyapunov-Schmidt reduction. And this is what this theorem here says, that the existence criterion for fronts of this small speed is equivalent to solving an algebraic equation called capital gamma with an index epsilon for the parameter epsilon that depends on this velocity parameter c. And whenever you solve this algebraic equation, you are guaranteed to have a front solution. And this, the next step in this analysis is to say more about how this function looks like. And here we can talk about how this function looks like in the singular limit epsilon equal to 0. And then it's very explicit. In this singular limit, it's looking like here. So there's this g function, which is the coupling function, appearing, evaluated at a particular point called v sharp. And v sharp is a vector with components that can be very explicitly written in this form. And then there's kind of an offset in addition, which is of this form. So ultimately, this is a very explicit function, and you can analyze it quite nicely to figure out what there is. And the abstract way that we formulate it here is that we can realize any Taylor polynomial of gamma 0 of degree 2n if only we are allowed to choose this coupling function to be of this quadratic nature. Right? So what this means is that if you tell me what Taylor polynomial you want to have so the first 2n components of the g function, you want something specified there, then I can give you parameters gamma, alpha j, and beta j to realize that.
Yes.
Yeah, and that means,
may I ask a question?
Sure,
So,
yes.
Essentially, you're looking at the bifurcation problem from that sort of inverse bifurcation problem in a sense, right? You're giving us the bifurcation curve, if I understand correctly.
Yeah.
And then you're telling us there exists a quadratic nonlinearity that realizes this.
Yeah, that's one way to think of it. Yeah.
Wow. Okay, very nice. Thank
you.
It's
not, I mean, well, it sounds more fancy than it is, but in this particular case, one can very explicitly analyze everything. And there's also this epsilon involved, right? So first of all, I'm saying here in the singular limit epsilon equal to 0, everything is very explicitly under control. And but for the PDE, you need epsilon to be positive. And then there is a regular perturbation of this.
Yes.
So in that sense, it's still under control, but it's kind of a two-stage process.
Okay.
And it's still true. So it's still true that for the PDE, kind of this type of coupling function is sufficient to realize, in more fancy words, any scalar singularity. So we can embed a butterfly catastrophe or a swallowtail catastrophe or whatever you like. Yeah, this is quite nice. And we'll see a little bit more about this in a moment. Okay, so this is just saying about the existence problem of fronts. And let me now explain a bit more how this front can be thought of in terms of this Allen-Cahn equation. So the scalar Allen-Cahn equation is very simple in a way, and has been introduced as a phase field model for phase separation. It's the simplest kind of phase separation where you have two phases of a material or so, which are normalized to -1 and +1. And these phases appear in this equation here as equilibrium points. Yeah? So if I just set everything to 1 or -1, then this is a root of this nonlinearity here, or of this part here, and these terms are then both 0 as well. So these are solutions, and they have they generate these plateaus here. These are these states, and then there are interfaces in between. And kind of an energetic viewpoint of this equation is that it's an L2 gradient flow with a double well potential. So this here is the L2 gradient, and the energy functional has this Dirichlet energy and then a potential. And this potential is the primitive of this cubic. And that generates this form here on the right-hand side, a double well potential with a minima at +1 and -1. And so what happens is if you basically take random initial data, you wait a moment, and then there's phases forming of this form near +1 and -1, and then interfaces in between, and then there's a slow coarsening process. But if you are taking the data such that you are only on the left side in this infinite space near -1 and on the right near +1, then there's a single interface, and this interface is just stationary and it has an explicit form as a tanh. And here you see also this gradient involvement of the epsilon again, that when epsilon gets smaller, the gradient gets larger and it gets very sharp. So in a way, this is a sharp interface formation. That's the energy viewpoint. And one can put this a little bit further to get intuition about what happens in the system that I talked about. Because if you perturb this and you introduce a flux, then that can be done in the following way. You just add a constant term here. And if you add this constant term here, you get a linear term in the potential energy. And the linear term in the potential energy means that these two equilibrium points are no longer on the same energy level, but there's a preference in this way to +1. And that means that if you have this single interface, you would expect, at least from this energy viewpoint, that the interface is moving to the left, because this here is energetically more favorable, the +1 state. And indeed, you can show this because there's an explicit solution in this case called the Huxley wave. But this energetic viewpoint is interesting and helpful because this is foreshadowing that this coupling that we are doing has the potential to generate something like this. So let me come back to our classical, this class of models that I was talking about. And here, just for the case n equal to 1, just one component, I have this epsilon g term in addition to the Allen-Cahn, which solves this heat equation, as I said before. And now one can understand in a way that this here is like a flux term locally, and it has then the potential to move this front back and forth, potentially. Yeah, so that's what we're after, or that's the way we think about it, that this coupling generates or realizes kind of front dynamics, and we call these objects dynamic fronts. And these equations have been studied a lot, as I said. I just want to acknowledge here, in particular for n equal to 1, work by this Japanese school, which also was for more general equations in the 80s and 90s in particular. And then for n equal to 2, this is this motivation from the gas discharge model by Purwins. Peter van Heister has written his PhD thesis on it, actually, but in a different scaling of this tau. So that's kind of another thing that enters here that is important. And Arjen Duhlmann, Tasso Karpa, and many others have worked on this as well, also Japanese, and probably I'm not, this is by no means complete. So many people have looked at this class of equations. And here we're looking at this particular regime where this timescale parameter is of this scale with respect to epsilon. And that makes a big difference, actually, it turns out. Okay, so I'm not sure about the backgrounds here, so let me talk a little bit about spectral stability for fronts or for traveling waves in general. So if we have a evolution equation that we can write formally as an ODE, but this F here can feature differential operators or so, like in this more abstract form of writing the system that I've just talked about, right? So the U is now thought of as a vector, and this d epsilon is a diffusion matrix. Here we have some nonlinearity, which can be epsilon dependent, and then there's a moving frame. And in the suitable moving frame, we might find an equilibrium point. Yeah, so in a function u star of x that solves this equation here, and that's then called a traveling wave in general. And these fronts that I was talking about are such. Now, if I want, after having solved the existence problem, which I alluded to how we can do it here, the next step would be to understand the stability properties. So then if you write it like this, you can actually justify this ODE-like analysis. We just linearize in this traveling wave right? So we get a linear operator by making sense of this differential here in a suitable function space. And then we can look at the eigenvalue problem associated to this linear operator. And this can basically be done also without function analysis overhead. You just write this down and you realize, okay, L is a reaction diffusion operator, say, and then this is actually nothing else than an ODE, a linear non-autonomous ODE. It's non-autonomous because the coefficients of this operator L depend through the shape of the traveling wave on space. And this is a very helpful perspective to look at this eigenvalue problem to solve for the spectrum. That's of course standard, but I just want to highlight this here. And in this context of these, or in most function spaces that are standard, say L2 or bounded uniform continuous functions, one gets a decomposition of the spectrum into what we call the essential spectrum and the point spectrum, which are distinguished by Fredholm properties. And that is again with the idea of bifurcation theory in mind, that we want to distinguish Fredholm zero from non-zero. So point spectrum is when this is the operator here. So L minus lambda is a Fredholm operator with index 0, and otherwise we call it essential spectrum. And this can actually be nicely understood in terms of the shape of the front or of the traveling waves, in particular for the fronts, because the essential spectrum is entirely resulting from the asymptotic states, if they are present, like in the fronts. On the left, we have the +1 and the -1 from the Allen-Cahn, and then there's a perturbation. And this is not going to be of our concern for the dynamics here, but we are concerned about the point spectrum. And the point spectrum for this front problem, that depends on the interface. In this case, is explicitly the interface, and the way that one formulates this, usually in this modern way, is as an Evans function. So we abstractly have some kind of generalized determinant, so to speak, whose roots give point spectrum. And the point spectrum, one aspect of the point spectrum can be understood very easily because we have translation symmetry, which means that if we look at this equation of the traveling wave existence once more, then we can differentiate with respect to space. Yeah, so what I'm doing here is I differentiate this equation with respect to x, the space variable. Then on the right-hand side, I get, by formally the chain rule, right, the linear operator that I was talking about before, multiplied with the space derivative of the traveling wave. And this solves this equation, which means that lambda equal to 0 is an eigenvalue, and the kernel contains the derivative of the traveling wave. Yeah, this is also sometimes called Goldstein mode. This is very standard in this context here. And in particular, the Evans function at 0 is 0. That's what this also means. So at least we know something about it. And then, well, how one actually does it in general, I won't go into too much detail. Let me just formulate it like this. So one tries to write the existence problem for eigenfunctions in a suitable way so that one has such a determinant type relation. Yeah, one way to do it is with exponential dichotomies. And as I said, I don't really want to go into too much detail, but one thing I want to point out here is that in this singularly perturbed context or the scale-separated context, there's a special structure appearing because the Evans function can be written as a product of two terms. And one term comes, the so-called fast Evans function, that comes from the Allen-Cahn front in this case. And the Allen-Cahn front in this case is stable, so this part here does not contribute to critical eigenvalues, except for the 0 eigenvalue, which is always there because of translation symmetry. And then there's a second factor in this, which comes from the interaction with the large-scale field somehow. And this is going to be the interesting part, which we want to understand, because we next want to understand bifurcations and stability properties of these fronts. Okay, so let me just look at the case when I have one additional component. And what one can show by doing this Evans function analysis is that not only is there always this translation 0 eigenvalue, but one can also generate a double 0 eigenvalue. And having a double 0 eigenvalue of an equilibrium point, you would expect, okay, and that's what we do here. We do center manifold reduction. There's a two-dimensional center manifold. And indeed, one can realize this here and see that the PDE reduces near such fronts to dynamic fronts, which are described by the center manifold of 2 dimensions, and the coordinates of the center manifold mean position and velocity. And because of the symmetry, again, there's a special way in which this is appearing, namely, we have this equation for the front position, and the z component here is then, or the z here is then meaning something like velocity, right? A scaled velocity. And the z component solves this equation, or an equation of this form rather, which does not depend on p again. And this is also called skew symmetry, because of this translation symmetry in the background that's kind of inherited on the center manifold, and it implies that the positions of the front do not matter for the velocity. So this equation here cannot depend on the position because we have translation symmetry, and this translation symmetry implies this kind of skew symmetric form. So in other words, the 2-dimensional center manifold is fibered by translation symmetry, and really this is just a 1-dimensional center manifold in a way, right? Because we are only interested in this one here. You can always reconstruct. Okay, and now we come a little bit of this interplay with the existence problem, but first let me mention that in a similar way as for the existence problem, we can show that we can realize any Taylor jet of this G function here at epsilon equal to 0, and then by regular perturbations, this is actually implying that we can realize any Taylor jet for G epsilon small. And that is, again, meaningful from a dynamics viewpoint because it means that we can basically prescribe any scalar ODE, right? So this is not very fancy, but it's kind of interesting. Okay, so let me look at a particular case. So I said earlier that for the existence problem, we can embed any singularity. In particular, the simplest one maybe is the so-called cusp singularity, which can be kind of geometrically formed like this. So we have a solution surface of this equation, which is on this side here, just monotone. So there's a unique solution for every parameter. So these 2 dimensions here mean 2 parameters of the problem. These are coefficients or some of the parameters I've mentioned before. And the vertical direction here can actually be interpreted as the z. So it's the speed. So on this side here, we always have one front with one chosen velocity. But then when we go to this side, we have actually 3. There's 3 fronts, 3 front equilibria, and they have different velocities. And we know that there's a 1-dimensional center manifold, which means that there's 1-dimensional dynamics in this vertical direction. So how these arrows can be understood is then if I take an initial condition close to this into equilibrium here in the middle, then the ODE dynamics will move it and I will just converge to the next one, right? Because a scalar ODE is just monotone. And here I have the same. And by the way, down here, there's oftentimes you might see the cusp represented in this form. So this is a 2-parameter plane, and the curves shown here are just the folds of this solution surface. Okay, so if I have this abstractly, I can now employ the results that I've presented and find particular parameters where this is really happening in the PDE. So I should be able to really do see this in the PDE dynamics. And indeed, this is a PDE simulation where the horizontal is time, vertically is the velocity. And what I'm doing here is exactly like in these arrows. I take an initial condition near this equilibrium point, which happens to be around minus 0.02. I perturb it a little bit in the one direction, and then I get a solution which looks like that for the velocity. I only show the velocity, right? So in the background, there's the PDE solved. I only show the velocity, and here's the other direction. And now we can lift this to the position of the front by just integrating. And that then looks like this. So here, because this is a negative value, for a long time, we're just going in this negative direction, and then eventually these two separate. And what I find funny about this is, right, by looking at the simulations for this time, you might think, oh, well, everything is moving to the negative direction in this case. But then somehow this blue curve decides, oh no, I want to change directions, and it shoots off and really goes the other way. Yeah. And this is kind of what it means that one has these embeddings, that you can design such dynamics in this system. Okay, so now let's look at more fields. Again, this is this class of equations I look at now with multiple components. And here's an abstract result of the same nature as I've just shown for n equal to 1. So first of all, I can realize an up to n+1 fold zero eigenvalue for the front. So I can choose parameters such that for each additional component of the slow fields, I can have one more multiplicity. And then this means that the PDE reduces, if one also does the symmetry reduction, to actually an n-dimensional center manifold for such dynamic fronts, which have then an equation, right? So there's an ODE on the center manifold, and it turns out that the ODE can be written as an nth order equation. Note that this is not true in general, right? Just because one has an n-dimensional ODE, it doesn't mean that one can write it as an nth order equation. But here this is always possible. And the reason for that is that these n+1 fold zero eigenvalue is actually a full Jordan block. This is very important if we want to understand center manifold dynamics near a equilibrium point. One thing you really need to know is what's the linear structure of, what's the linearization. And here it turns out that for this class of equations, it's always a full Jordan block. And that means that it's an nth order equation that you get. And it has,
I have a question here. So you have this very nice, can I ask a question? Hello?
Sorry, once more?
Can I ask a question? Hello? Can you hear me?
Yes.
Hello? Can you hear me?
Yeah.
Yes. Okay. I'm curious about this full Jordan chain. Is this because of your spatial nonlinearity, or it is from the separation of scales?
It's because of the separation of scales.
So it's very general. You can consider other nonlinearity, not just U minus Vj.
That's right.
Okay.
I mean, it doesn't depend on the nonlinearity here. It's not because of this particular cubic form. It's because of the scale separation, and also because of this kind of seemingly weak coupling here. So it's, in a way, it's a combination of the scale separation and the coupling structure.
I see.
I mean, it's a good question, and maybe I'll have time to say a little bit more about it. But for a while, we were unsure about what happens. And then it just turns out that you can, for this class of equations, always solve the Jordan chain. And morally, it's because you only have the translation symmetry, basically. So there's only one geometric direction, roughly speaking. Yeah. So, for example, if you would take two fronts, you have one front on the left and another, or two interfaces, I should say, then you might know that in kind of more generality, if they are far away from each other, there's a so-called weak interaction theory, which says that you have two zero eigenvalues, or two small eigenvalues to expect. One is from the joint translation and one is from the relative translation. Yeah, and the same thing happens here. So if you want to generate a higher geometric kernel, you have to look, for example, to multiple interfaces. But if you start with a single interface, there's only kind of one geometric direction. I know this is not very rigorous, but for this particular system, let me answer it again. It's because of the scale separation, because of the coupling structure. And I would actually guess that it's not even this epsilon factory is not even relevant. It's really the scale separation that's behind this. Okay, and again, we have such a kind of realization or an embedding type result that we can realize any small Taylor jet of this ODE up to a certain order, right? So this is here the length of this Jordan chain here. And this can be realized by choosing this coupling function, right? So the coupling function is our control, basically. We can choose this coupling function in such a way that we know what the ODE on the center manifold does. And from an abstract viewpoint, this is basically clear, and of course also these parameters. But the key thing is that in this particular system, one can do all this quite explicitly. And that's why one has so much control over it. Okay, and another take-home message here is that for n slow components, you have an up to n-dimensional dynamics of these fronts. One more word about the spectrum. So what happens in the limit epsilon to 0 is that from this heat equation part, we get kind of a heat equation type spectrum. This is this light blue here. This is indicating the essential spectrum. I mentioned that before, that the essential spectrum is epsilon squared close to 0. And that is, for the limit epsilon going to 0, we are kind of in this position. That comes basically from these heat equations, as I said. And then there is the Allen-Cahn equation itself, which has the front that we know from this interface, the explicit tanh solution, and that has a translation 0 eigenvalue. So we can think of it as in a limit epsilon to 0, there's this essential spectrum and an embedded 0 eigenvalue. And now when we turn on epsilon, what happens is that the epsilon, the essential spectrum retracts from 0, it moves to the left, but it kind of spits out up to n eigenvalues, which are close to 0. And these n eigenvalues form this center manifold. They are kind of the basis of the center manifold. And we have quite good control over the location of these eigenvalues. Okay, so that's about this center manifold reduction part. Again, because of the symmetry, there is this skew symmetry. So one has a position which can be inferred from this equation here. All right, so here's another result. Sorry that I just showed these results, but I think much more is going to be difficult, and I just want to get kind of some take-home messages across. So we were talking about the dynamics for a moment, and now the question is, how do we know about these eigenvalues? And here's just kind of a glimpse as to what happens in terms of this Evans function I've talked about before. One can show that the eigenvalues that are relevant for the stability are all of this epsilon squared scale, and they solve this slow Evans function I mentioned before, which is called E here now. And this slow Evans function in the limit epsilon to 0 has a very explicit form again, which is somewhat reminiscent of the existence problem. But here the lambda is our decisive parameter, and that's this complex eigenvalue parameter. So remember, this kind of comes from we solve the eigenvalue problem, and then we get the eigenvalue as a parameter in this. And whenever we find a root of this function, so this E is 0, sorry, I think there's a hat missing in these, then we have an eigenvalue. And this is a rather explicit function. On the other hand, it is complex analytically also interesting, because here's the lambda also appearing, right? It appears in two places, or in each summand, it appears here. And because all these coefficients are all positive, it means that when lambda is real negative, then we are on the branch cut of this primary or this principal square root. So complex analytically, there is on the negative half lines multiple branch cuts on top of each other, and we are, however, only interested in the eigenvalues away from this. But it's not so easy to analyze this function actually and find out how many solutions there are, for example. Nevertheless, for solutions near 0, we can realize any location of roots already using, again, this quadratic coupling function. So the way to think of it is, you tell me where you want these n eigenvalues to be, respecting complex conjugation symmetry, then I can give you parameters gamma, alpha j, and beta j to realize that. Okay, now comes the caveat. The caveat of this is that we don't have this completely under control yet. I'm optimistic that we will be able to do this in general, but when n is bigger than 4 or larger than 3, strictly larger than 3, then we do not really know what happens in terms of other eigenvalues than those that we have under control here. So this function here might have other solutions that we don't really know about, unfortunately. But at least for this n less than or equal to 3, we can say that there is a constant c, and sorry, here's an epsilon squared, this is 2 missing. We can say that in this critical region, there are no other eigenvalues. So that in particular rules out that there are other unstable eigenvalues. Okay, so this is what one can do in this system, and now let's kind of harvest what this can be, what this can do for us in 3 dimensions. Now we now know that n gives us the number of dimensions of the reduced center manifold. We want, and the title I had is chaotic, so we need at least 3 dimensions for an ODE to be chaotic and an autonomous ODE. And indeed, one can show the following here, that there are parameter values such that the front ODE possesses a Shilnikov homoclinic orbit, which is transverse in the parameters. And okay, this is kind of this dynamics jargon. So there's a particular solution, so-called Shilnikov homoclinic orbit, and this has been studied quite a lot. And it is known that if the ODE admits in parameters to break this homoclinic orbit, then one has chaotic attractors. So this is what we are building on this kind of long-standing ODE theory. In particular, it means that the front motion dynamics contains chaotic attractors. So this front motion, the self-organized front motion, right? I remind you the way that I think of it is like there's the self-organized energy flux between the scales, right? There's a large scale from the V, there's this sharp interface, small scale, and it is between these scales that the energy is exchanged. And this exchange of energy can be producing chaotic motion. That's the way that I think of it. Okay, just some ingredients of the proof. What I already said, we have good control over the existence problem. That's important. We have pretty good control over the stability problem as well. The key point 1 is that we can fully control the location of eigenvalues near 0. The key point 2 is that multiple 0 eigenvalues come with a full Jordan chain. And this is what helps us to realize that we can get this ODE form here. Yeah, so here's a constant parameter. Now lambda is not an eigenvalue. I just used this because of a certain reference that comes in a moment. So there are these 3 parameters, lambda, mu, and nu. And there is this coefficient A here. And because of all the things we know of this control I mentioned, we can actually say that we can produce parameters of the function g and of this tors and d's such that this coefficient A is guaranteed to be non-zero. And at the same time, we can realize that these parameters here fill an open neighborhood of 0 by perturbations of the parameters. Yeah, and these 2 ingredients are sufficient to, I mean, first of all, we can do this with this quadratic function, coupling function g. And if one has all this together, then one can apply an ODE result by Ibanez and Rodriguez about this local birth of chaos, which does the job for us. So they analyze this ODE here under these conditions and say that if you have those conditions, then in the unfolding of these parameters here, you find a Shilnikov homoclinic orbit and you break it transversely and have complicated and chaotic dynamics. So that's the way that we build on this result. Okay, so this is abstract. So what does this mean in terms of, I also want to see something numerically. And then that's the problem, because this type of ODE analysis also implies that you have countably many chaotic attractors, okay, but the basin of attraction is extremely small. It's actually exponentially small in these parameters. So you will basically never be able to see it numerically. This is the caveat. But on the other hand, one can do some numerics outside this regime. And here I'd like to just tell you how we did it. Once we had this result, we saw, okay, we know that we can't really see it, but maybe in the neighborhood, one can still see something interesting. And then there's a choice of parameters going on and so on. So let me guide you through this a little bit. What I'm showing here is there's a certain parameter alpha 1. I think I forgot what it is exactly. It's one. I think it's a linear coefficient of this coupling function g. And vertically, it's the velocity. So it's a bit like one parameter slice in this cusp type situation I showed before. But now there are these 4 branches. And these 4 branches are a result of a perturbation of a transcritical bifurcation in 2 ways. So the black and the red are for different values of epsilon in this case. And no, so yeah, for different values of epsilon in this case. And it's because epsilon is non-zero that we do not get the transcritical bifurcation exactly, but it's kind of broken up. But you should think of this cross here. And whenever you have the transcritical two linear branches crossing, you can break it in two ways. One is like this, and one is where the black curves are, and one is where the red curves are. And now we focus on this region here, because this is a fold point. We focus on this fold point, and it looks like so by enlarging. Yeah. So by the way, this is so-called numerical continuation done for this PDE. So I compute in the PDE numerically where the fronts are, and then track how they go in parameter space. And this gives rise to these bifurcation diagrams. And here I labeled 4 of these points. And also there's this thick curve here and the thin curve. And thick means stable, thick means unstable. Sorry, thick means stable, thin means unstable. So what happens here, if you just stare at it, it means you have an unstable front. It goes to a fold, then it becomes stable, and then it becomes unstable again. Yeah, so a fold means there's a one eigenvalue crossing, so it crosses from unstable to stable. And then here I have along the branch another destabilization. And that's actually something we want to focus on now, because this point here, if I look at the spectrum, also computed numerically now, I see that it's a complex conjugate pair of eigenvalues. So there's actually a Hopf bifurcation going on. So what we have here is kind of, we are in the neighborhood of a saddle node Hopf bifurcation. And a saddle node Hopf bifurcation is known to be a birthplace of chaos as well. And so we're optimistic and say, okay, let's look what happens if we just do some numerics. So what I'm doing here is I look at the vicinity of this point 60, which is a front solution, and I perturb from this front solution, and I plot the resulting dynamics. So here's time horizontally, and space, and vertically is the velocity of the front. So I'm plotting how the velocity of the front is doing, and it's oscillating, right? So in terms of the center manifold, it means there's a periodic orbit. It can be shown here in terms of this velocity and the acceleration. So what happens here in this scenario seems to be that there's a branch of periodic orbits coming out, which I didn't compute here. There's a branch of periodic orbits, and it is stable, and it is the equilibrium point here. When perturbing from it, one is in the basin of attraction of this periodic orbit. Now, if I go to point 66 and I do the same thing, I notice this. Yeah, and from an ODE viewpoint, you can now guess, okay, between 60 and 66, there's probably a period doubling bifurcation. Yeah, because now I have two frequencies here in these oscillations, and if I plot it in the plane, it looks like this. And then, oh, okay, now we're in business, because there's now a good chance that maybe there's a torus bifurcation, and a torus bifurcation is giving rise to chaotic dynamics. So if I go to point 70 now, it seems that there was such a torus bifurcation, because the simulation at point 70 gives this dynamics. And if I plot it in the diagram or in this plane, it looks like that. And this is kind of very convincing of a chaotic attractor, I would say. And indeed, if we plot the front positions, or rather the deviation from the mean position, so space is horizontal, time goes up, we see such a jaggy motion, and that's kind of evidence for chaotic dynamics, I would say. Okay, so this is kind of the upshot. Nearly finished, that we have this theoretical result for the existence of chaotic attractors, but they are basically invisible in the numerics. But in the vicinity of it, and what we've done here was following up earlier work by other people that works also for the PDE, we find nevertheless chaotic dynamics. However, this is not provably chaotic from a rigorous viewpoint. Okay, before closing, I just want to briefly make an advertisement. There's a new or relatively new journal. Last year it started, the Journal of Nonlinear Waves. And if you have an interesting paper, you can consider submitting it there. All right, and with this, I thank you very much for your attention, and I'm happy to take questions.
Thank you very much, Jens. So feel free to open up your mics and ask questions.
So maybe let me start with a question. So you mentioned that the basing of a chaos attractor is exponentially small. This
Yes.
is exotic to me. I don't know why. Can you explain it a little bit more?
Yeah, I don't really have a good picture for it, but let me explain it in words. That what happens is that you have this Shilnikov homoclinic orbit,
Yes.
and you break the homoclinic orbit,
Yes.
right? So, and it is known that if you have such a homoclinic bifurcation, you basically create in the return map, you create a homoclinic, you create a transverse homoclinic orbit.
Yes. Yes.
And such a transverse homoclinic orbit from this breaking is known that this is exponentially sensitive. So the thing is that the unstable manifold from the homoclinic orbit that is involved in the homoclinic orbit is extremely sensitive in parameters. Yeah, so if you break the homoclinic just a little bit, you have a huge deviation eventually. Right, so it is this exponential smallness phenomenon in transverse homoclinic orbits, which is behind it.
So this is a very general result from Shilnikov chaos.
Yeah, this is very general. It's well known, and I mean, it's not only that this is exponentially small in parameters, but it is also the other thing why it's difficult to observe numerically is that it's very slow. It's very slow in time.
Okay, I see.
And that's why in the numerical simulations, you really need a lot of time steps to see kind of a good portion of this chaotic attractor, even in the away from this, right? So there are basically two things coming together. One is that it's extremely sensitive in parameters, and that means the basins of attraction are very small, and you're very unlikely to sit in one. And the other is that it's slow in time.
Yes, thank you.
Further questions? Otherwise, I will ask myself. So you mentioned that you can embed any dynamics in this G0, right? Like you can pick G0.
Small G, right?
Yeah.
Yes. My question is regarding, well, how to perturb for small G, because it's not clear to me that you should be able to just prescribe anything. I agree.
I mean, let me make a kind of the rain check here. Anything is possible in 1D.
In 1D.
Right. In 1D. So you have a scalar ODE, and we can realize any scalar ODE near the 0 point, right? So that is not really an obstacle, but it's near the equilibrium point, and in the you can kind of create a neighborhood of the equilibrium point, and in that neighborhood you can have anything one-dimensional. Yeah? So that's not very strong. It's just one-dimensional.
Okay. Then this is a consequence that of the fact that all one-dimensional vector fields are gradient in a certain sense.
Yeah, maybe that's one way to think of it. Here, I would say it's a consequence of the fact that we have transversality in the parameters of the Taylor jets, and that's sufficient in this case. And in higher dimensions, it's more complicated. I mean, there's probably more one can say. For example, in 2 dimensions, we can also very explicitly analyze and unfold Hopf bifurcations. That's something we've done in an earlier work. And there, but the obstacle to realize general dynamics in 2D or in higher D is again this Jordan chain. So all the equations that we can produce are nth order equations. I mean, maybe that's one way to say it, right? If I come back to this slide here, that we can produce any G function in this nth order equation. Okay, that's true. But it's not clear how general the dynamics is that you get, right? That's the obstacle in a way. But if you are just interested in nth order dynamics, then we can do anything even in higher dimensions, right? So in nth order, as I said.
And then of course these Shilnikov chaos is a structurally stable feature, right? So
Yes.
prescribe
Yes.
it at D0, it should stay there for small
Yes,
experiments.
exactly. I mean, the structural stability is a very important aspect, right? Because we have this control only in the singular limit epsilon equal to 0, and everything we do must, for perturbing with respect to epsilon, we need structural stability. Yeah. And indeed, Shilnikov homoclinic orbits and the chaotic attractors that result from it are structurally stable. So they persist under sufficiently small perturbations. And yeah, I mean, the technical sides are a little bit subtle that one has to control really carefully that all these perturbations are small enough, so to speak, right?
Oh, it's amazing. It's really interesting. Yeah.
And in this slide, I have one question or one request, and I am interested in stabilization of nonlinear wave. And here you see you have unstable eigenvalues, and there's a notion of Pyrrhus control, non-invasive control. Do you think that it's possible in your setting to make the unstable eigenmodes to be stable, or to stabilization?
Probably there's at least something one can do. And I should say that this is actually structurally related to what Fritz Fährmann and Juliette,
Isabel Schneider?
Yeah, exactly. Fritz Fährmann and Isabel Schneider did for the pulses.
Ah.
Yeah, and I would say this is perhaps easier, actually. I think this is easier than the pulses. Yeah, this is, I'm pretty sure this is easier here.
Why? I am curious about this. Yeah, why?
Yeah, because the what they did for the pulses was in Gira-Meinhardt, if I remember well.
Yes.
Right? The Gira-Meinhardt model. And so there's two things. One thing is that Gira-Meinhardt is more complicated because it has both equations are nonlinear. And then even though you can still do this existence and Evans function analysis, it's more complicated actually. This is also the other simplifying factor here is that we are only looking at fronts. And if you have a front, then in the construction of the singular orbit, it's easier than a pulse.
Yes.
I don't know how familiar you are with it, but if you construct a pulse in this singular limit, you have two pieces. You have more matching to do.
Yeah. True.
And here we have less matching to do, so to speak, right? That's one way to think of it. On this, I mean, what's behind it is this geometric singular perturbation theory, where you have slow manifolds and you perturb them, and the more jumps between slow and fast you have, the more complicated it gets.
Yeah.
And here we have only one jump, so it's as easy as it can get.
Yeah. And I read a paper of Fritz and Isabella. They don't really use the Pyrrhus control. Their control is require a lot of knowledge on the target pulse. So I think this is one of the main reasons is because their pulse is too difficult. But I am thinking maybe your setting is a good it's a good equation for them to really apply Pyrrhus control. Okay, interesting.
Yeah. Perhaps one further question regarding this last picture where you showed us what could be chaos, but which is hard to observe. When you started to have this period doubling, yes. Do you think there is some sort of period doubling cascade going on here?
Well, I mean, in these transitions to chaos and ODEs, right? The typical thing I would say is not a cascade, but that you have two stages. You have a torus formation, torus bifurcation, which is like two frequencies. And then here you already have these two frequencies, right? And then these two frequencies, there's like a Nymark-Zucker bifurcation or something like this, so that you have a torus. On the torus, you get chaotic dynamics, or you have a breaking of the torus. And so well, I mean, this is, I think, going back also to this transitions to chaos stuff, that although this period doubling cascade is kind of a nice observation in maps, it's not necessarily the typical route that you have in ODEs. Because the more typical thing is this torus bifurcation. I don't know too much about it, I must say, but basically what the takeaway message I got from it is that one shouldn't expect cascades, but you should expect two stages and then you're already chaotic.
Oh, wow.
But in a kind of weak sense, right? Because it's a incommensurate frequency chaos. And I should say that what we're working on right now is to get the Lorentz attractor, actually. So this is something else. So the types of chaos in ODE, right? There's different types of chaotic attractors and different structural features of these attractors. And one type of attractor, which is very robust and kind of maybe the hallmark of chaotic dynamics in some sense, is the Lorentz attractor. But this cannot be reached from this particular shape of equations because of this Jordan chain constraint. Because there's no nth order equation perturbation that gives a Lorentz attractor. You really need to have another geometric eigenfunction, but that can be done in principle. So there's hope that one can get there. Yeah.
Nice. Oh, it looks very good.
Yes, amazing.
Thank you.
Yes, so do we have any further questions from the audience?
Hello.
Hi, yes.
Yeah, Professor Zhang, yeah, please.
Hello, and thank you for your nice talk. I have a small question. Maybe your page 6, your theory of your preprint.
Yeah.
Okay, I don't see the page numbers, unfortunately.
Sorry. It's an expression about the Evans function. Maybe next one. You have a formula E0 lambda.
Evans function.
Yeah, Evans function.
Yeah, okay.
Like your preprint. Maybe next one.
Next one.
Oh, okay. I'm sorry. The Evans function. Yeah, now I understand.
Evans function part.
Yep. Wait a minute.
Forget which page.
Yeah.
This one. Yes. So my question is, of course, this involves some detailed computation, but how to calculate such E0 lambda? Because if epsilon is 0, if epsilon is 0, it looks no phi component here.
Yeah. Well, I mean, one can do all of this formally by just solving the eigenvalue problem. So you look at the linearization of these equations, and then you just assume that everything works as you like. One particular ingredient that enters both in the existence and for this Evans function is that the V equations are linear. So you get solutions, you get kind of the solutions. Maybe I should, sorry, I think I go to this here. So what you see is this part of the solution on the left. This is actually an exponential function, almost exactly. So the smaller epsilon is, the more this function is an explicit exponential. And also on this side, it's exponential because it's just from the linear equation V here. So these are exponentials. And then you have in the middle a kind of matching condition. And that's why I'm trying to answer it this way. So you can try to write down the existence problem of the eigenfunction. Then you get these exponentials and you get that they have to be continuous in here. And by implementing those conditions, you get, for example, what's on this slide, this type of term that comes out automatically from this consideration. And this is very similar in the Evans function. So the reason that these terms appear is because, or these have this explicit form, is because of the linear nature of the equation on both sides of the interface. Right? On the left of the interface, it's linear. On the right of the interface, it's linear, in the limit epsilon to 0. And that admits this explicit computation. And maybe I can go to some other slide to say one more word about it. Sorry. Right, so here one has, again, these square root type terms. They come from this linear equations. The eigenvalue problem is similarly a linear equation on either side of the interface. And well, I have one backup slide where I explained a little bit about this. Here. Okay, so
backup slides.
yeah, so this is how the linear operator looks like. Maybe you just focus on this for the moment. So this is how the linearization looks like. It is a block operator where on the upper left one has this Sturm-Liouville operator. And then there's these coupling terms. On the lower right block, it's from this stabilized heat equation. And here I'm explaining or trying to explain how one would solve the Jordan chain and why it's a full Jordan chain. But similarly, it's for the eigenfunctions or for the expression of the Evans function itself that one exploits this explicit nature of the operators to solve for the eigenfunction. And then in the matching of it, you get these algebraic constraints. That's kind of what's behind it. But if you want to make this rigorous, the way that we do it is that we go to this more abstract Evans function formulation by a exponential dichotomies and transversality properties and so on. But if you just want to know how the Evans function looks like, then you can compute it kind of explicitly by hand because of this nature, right? And so one thing that I'm trying to explain here, but you can look at the second block of these equations here, these lower ones. They are the good ones because here you have a stabilized heat equation, right? So this operator is actually invertible because of this -1. So we can solve this second part of these equations, which I call psi v here, by just inverting this part, right? And then you have your inhomogeneity for the first part. So you solve the second, you substitute the result in the first. And that gives this equation here. And this equation is almost a Sturm-Liouville equation, except for this non-local operator here. But one can compute things still explicitly. Yeah. I'm not sure that this was a very good explanation, but this is how one gets the Evans function. And I mean, in the papers, it might not be so easy to see, but in some of the papers, we have a kind of an explanation of the direct computation. So, for example, in I think in this one, in this one here, where we do this Bogdanov-Tarkins embedding, there's kind of the appendix explains how to do this computation explicitly. And also in this preprint, which is waiting for referee reports for a year now, it's explained.
Yes. Thank you. Thank you.
Yeah. Could you go back to the slide of this Evans function? This match you just showed us. Yes. No. The one, the backup slide.
Oh, the Jordan chain. Yeah.
The Jordan chain. Yeah. Yes. I was thinking maybe the Jordan chain, this like almost decoupling comes from the fact that you choose n different time scale, like it's tau j, epsilon, and tau j. But to the left-hand side, I just saw epsilon, and where the tau j, it seems that tau j does not play a role here, right? Oh, there.
Well, it enters here, right? It enters here on this right-hand side, and it does not. It's not essential. Well, I mean, there are some conditions for the solvability actually that require that they, or for certain types of this. Well, let me put it this way: for the Jordan chain, it doesn't matter.
Oh.
For the Jordan chain, it doesn't matter, but there are some conditions coming up that one has to have different relations. I mean, there's certain relations between the DJs and the TORJs coming up in order to get this nth order 0.
I see.
Indeed. So there is a way in which these parameters do matter, but it's not very transparent. It comes after this step. So if you solve these equations. Yeah.
And if I deliberately choose two of the tau j the same,
yes,
this Jordan chain structure still there, or
yeah,
they
yeah,
are
yeah,
like
still there. Yeah.
yeah, still there.
Yeah.
So,
For two,
okay,
that's
okay,
no
I
problem. It's more complicated. It doesn't appear on this level, right? It's
Okay,
more
okay.
appearing that if you want to solve these equations, you have to have also the existence problem suitably, and the tau j's need not. I don't want to say anything wrong, but there is one result where we need the tau j's to be different from each other, indeed. But I don't think it's necessary for the Jordan chain.
I see. So the Jordan chain really comes from the phase and the slow time scale, but whether they are different slow scale, it doesn't matter. Like they are.
Yeah, I mean, as I say, for the production of an nth order zero or an n-fold zero, one needs to obey certain constraints between the tau j's and the dj's. So it's more that the interaction between these spatial scales and the temporal scales, there's a certain constraint, but it's more complicated than just saying they are not equal. But yeah, that's what I remember from it. And
I see. Okay, delicate. Yeah. But interesting. Yes. Okay. Interesting.
Yeah, I think, yeah, right. So these relations that I've just mentioned before, they are necessary to have transversality in order to realize this for epsilon positive. Yeah, so that's how it enters. And there is, the simplest situations, they are different, but there's a relation, I think it's of the form tau j times dj summed up, cannot be zero.
So you need that condition.
Sorry, cannot be the same. Yeah, there's an algebraic relation between the taus that involves products. So tau j times dj, yeah, tau j times dj must be different, I think. They must be different, but not the individual ones.
Okay. So you need this algebraic relation to apply the Fenichel theorem, or like to recover the small epsilon case, or
it's not directly Fenichel. It is because what we do is that we solve these equations in the limit.
You just solve this. Okay, sorry.
It's purely on the level of the algebraic equations that we need to ensure. We need to ensure that whatever we do for epsilon equal to 0 can be transferred to epsilon positive, right? So this is kind of a transversality on this algebraic level. So it's more openness, right? So that the parameters are sufficient to realize any perturbation, so that one has an open set of in parameter space.
Okay, thank you.
Very nice. Good. And then, if there are no further questions, I think we could close the session here. So let us thank the speaker again. Thank you very much.
Thank you.